Welcome to the second of two video lectures on the time value of money. The previous video was on the present and future values of an amount. This one covers the present and future values of annuities. If you haven't watched that one yet, please do so before watching this one. In this video, I'll assume that you've learned the basics of using time value of money formulas, templates, and tables. There's a link to that video in the description box below. The root word of annuity is annual, which of course means yearly. With a financial instrument known as an annuity, you deposit a specific amount of money into an account at the end of every year, or a specific amount of income is paid to you from an account every year. Let's consider the following example. Suppose you made an annual deposit of $100 into a money market account at your bank every year. That account will pay 10% annually. Here's your deposit of $100 made at the end of year one. The height of the box represents the amount of stacked up dollars in the account. Now keep in mind that with a conventional annuity, which for us will be our default case, the deposit is made at the end of the year. So the deposit, represented by that little box of stacked up dollar bills, was made at 11:59 p.m. on December 31st of the year in which you started saving. And so therefore, no interest whatsoever was earned in year one. An annuity for which the deposit or payment is made at the beginning of the year is known as an annuity due. These are special exceptions, and we won't deal with them very much in this class this semester. So there's our money stacked up in some bank vault somewhere at the end of year one, $100. By the end of year two, however, that stack has earned $10, which resulted from the 10% interest rate that the bank paid. Remember now, we're dealing with annual deposits, annuities. So here is the next deposit or payment made at 11:59 p.m. on December 31st of the second year that you started saving. So as you can see, by the end of year two, we have $210 in the account. Here's the interest that was earned by the end of year three, $21. That's 10% of the money that sat in the account for all of year three, from the end of year two until the end of year three. And here's the deposit for year three, made on December 31st, 11:59 p.m. of year three. After having made that deposit, there is now $331 in the account. Now this $331 will sit in the account and earn 10% interest for the entirety of year four, from the end of year three until the end of year four. By the end of year four, after having earned $33.10 in interest, and after the annual deposit of $100 has been made at the end of the year, there is now $464.10 in the account. What we'd like to know is how much money would be in the account by the end of year 20. So therefore, we will need to compute the future value of an annuity. Here's the formula for computing the future value of an annuity. It's a little more complicated than the formula for the future value of an amount. I won't bother deriving it for you here, but if you're interested in a mathematical derivation of this formula, post a comment in the time value of money form on the discussions board, and I'll provide you with one. The term annuity in this formula represents the annual deposit that is made by you, or the annual payment to you. From this point on, we'll just designate this variable in the formula PMT, which would stand for payment. The letter R will represent the rate of return. If you're making deposits into a money market account, R would represent the interest rate. Or if this financial instrument is generating some other form of revenue, such as dividends or profits, the R term would represent the annual revenue received as a proportion of, that is, divided by, the principal, the total amount you deposited. And the N would represent the amount of time in years. So now let's go back to our original problem. If we deposited $100 at the end of every year into an account that pays 10% annually, how much money will be in the account at the end of 20 years? Let's plug in the values we know into our formula and find out. Notice that the 10% rate is expressed as a decimal rather than a percentage. So in the parentheses, we have 1 plus 0.1, which of course is 1.1, and 1.1 to the 20th power is 6.7275, and when we subtract 1 from that, we get 5.7275. Then 5.7275 divided by 0.1 is 57.275. And when we multiply that by $100, we get $5,727.50. If you deposit $100 into an account that pays a rate of return of 10% every year for the next 20 years, that's how much money will be in the account. Rather than using this formula, which could be a big pain if you didn't have an exponent function on your calculator, you may wish to use the future value of an annuity table. This number here, 57.275, is called the future value interest factor of an annuity, the FVIFA, and it's already been computed for you in the future value of an annuity tables. All you need to do is find it. Here's the future value of an annuity table. Make sure when you're finding the FVIFA, you're using the correct table. It's easy to use the future value of an amount table instead. Lots of test points have been lost because the wrong table was used. Okay, so let's set up the template for computing the future value of an annuity by use of the table. Notice that it's very similar to the template for the future value of an amount, except instead of multiplying the FVIFA by the present value, as we did for an amount, we multiply it by the annual payment. There's the FVIFA. That's what you're seeing in the table. To find the relevant FVIFA, we simply find where the coordinates of the two variables intersect. Here's the 10% column, and here is the 20-year row. And here's where they intersect. As you can see, the future value interest factor of an annuity, the FVIFA, where R is 10% and N is 20 years, is 57.2750, just as we had computed it by the formula. So we take that value, 57.275, multiply it by our annual deposit of $100, and we see that $5,727.50 will be in that account at the end of the 20-year period, which is exactly what we got from the formula. Sometimes tables are published with the coefficients having only 3 decimal places rather than 4, as in this case. The FVIFA, therefore, will not be quite as accurate as they are in this table. For that reason, small rounding errors are permissible in time value of money problems. But just use the tables that you can download from Module 2. All of those coefficients are extended to 4 decimal places, so this issue shouldn't be a problem. The term small, as in small rounding error, is a completely subjective concept. How much of an inaccuracy can be attributed to a rounding error? That's up for the professor administering the test to determine. Speaking for myself, and I've seen this in many other cases as well, an inaccuracy of 1% or less can be considered a rounding error. Now let's try another problem, but with a little bit of a twist. If you deposited $5,000 annually into an account that would pay you an 8% rate of return on investment, how long would it take you to accumulate $200,000? Here's a future value of an annuity problem, and you can tell because you're depositing $5,000 annually. What's different is that you know both the deposit amount and the future value, and you also know the rate of return. So you simply set up the future value of an annuity template and solve for n, the number of time periods. Here's our future value of an annuity template. Let's just fill in the values for the variables that we know. And here are those values filled in. Let's use a little 8th grade algebra to manipulate this equation. What we did here is to move the $5,000 from the right-hand side of the equation to the left-hand side of the equation and express that ratio, $200,000 divided by $5,000, as a whole number, 40. Notice that the dollar signs have disappeared from the left-hand side of the equation. That is, it's not $40, it's just 40. That's because the dollar signs appear in both the numerator and the denominator of this fraction, and thus they get canceled out. For example, $10 divided by $2 equals 5, not $5. $2 goes into $10 5 times, not $5 times. Those two dollar signs cancel each other out. Okay, so back to our problem. Here we have the template all set up and ready to roll. 40 is equal to FVIFA at 8% for n years. Remember, we're solving for n. So first, let's locate the 8% column. And so now, let's find a 40 somewhere in that column. Well, we're not going to find exactly 40, but let's find a number as close to 40 as we can get. There it is. That's about as close as we're going to come using the tables. Now all we have to do is go across the table to see how many compounding periods it takes to produce a future value interest factor of an annuity, an FVIFA, that close to 40. So we see that if you deposit $5,000 a year into an account earning 8%, it'll take about 19 years for that account to grow to $200,000. Let's do one more variation before we move on to the present value of an annuity. What rate of return would you need in order to turn a $1,000 annual deposit into $15,000 in 10 years? Obviously, if you were stuffing this deposit into a pillowcase, it would take you 15 years. But we're depositing it into an account that pays an annual return, which can be used to generate even more income in subsequent periods. What then will be the required rate of return to turn those $1,000 annual deposits into $15,000 in 10 years? Here's our future value of an annuity template. Again, we'll just fill in the values we know. Now that we have the values filled in, we can just use our future value of an annuity table to solve for R, the required rate of return. We'll just move that $1,000 to the other side of the equation so that we'll know what we're looking for on the table. So we'll just go across the 10-year row and look for a 15. There you go, 15.1929. That's close enough. From there, going up the column, we see that it's going to take a rate of return of about 9%. Now let's consider the present value of an annuity. Just as in the case with the present value of an amount, the trick with the present value of an annuity calculations is in choosing the appropriate discount rate. If we want to know the real or purchasing power value of some future amount, we simply use the anticipated average annual rate of inflation as the discount rate. But if we're comparing two values that we will receive in the future, we need to use something called the required rate of return. Again, there is a set of lecture notes in Module 2 describing the concept of the required rate of return, what it is, and why we would use it. Make sure you understand that concept thoroughly. Let's start with computing the real value of some stream of annual payments that you will receive in the future, expressed in terms of what a dollar will buy today. As you know, a dollar received in the future won't buy as much as a dollar will today because of inflation. A dollar received in the future might only buy what 80 cents would buy today. The present value of that future dollar would then be 80 cents. Here is the formula for computing the present value of an annuity. As you can see, it's going to be far easier to use the tables than a standard calculator. With a financial calculator, though, it's a breeze, and it'll be even more accurate than the tables. Let's do a problem. Assume you have a structured settlement from an insurance company to compensate you for the pain and suffering you experienced from an accident. Say, a safe fell on you as you were walking past an office building. A structured settlement is one that will pay you a fixed amount at regular intervals. Suppose that in this case, the insurance company will pay you $5,000 per year over the next 8 years. Also assume that the rate of inflation over the next 8 years will be 5%, although there's no way you have of actually knowing that. What is the purchasing power value of that settlement in terms of what a dollar will buy today? In other words, what is the present value of this annuity discounted at the anticipated rate of inflation? Let's fill in the values that we know. Here's our annual payment, and here are the rest of our values plugged in. But rather than doing all that math, let's just cut to the chase and use the present value of an annuity table. You can be confident that we'll get the same answer irrespective of the method that we use. Fortunately, that complicated expression in the red circle has already been computed for us. It's called the present value interest factor of an annuity, the PVIFA, and it's available in the present value of an annuity table. We'll see that in just a minute. So the present value of an annuity template would look like this in its general form. Rather than compute it, we just need to find it on the table. Again, here's the information we know. The annual payment is $5,000. Because we're looking for the real value of some future number of dollars, we'll use the rate of inflation, or more technically, the anticipated average annual rate of inflation as the discount rate, which in this case is 5%. And this stream of annual payments will be made over the next 8 years. Our PVIFA, therefore, is 6.4632. Then, when we plug that value into our template, we see then that the present value of the sum of those payments, the $5,000 per year for 8 years, which of course is $40,000 received in total, discounted at the anticipated rate of inflation, is $32,316. Using the present value of an annuity template is very valuable and helpful in making what I like to call nest egg calculations. A nest egg is a fund that is intended to finance a specific activity for a given period of time. Many people have retirement nest eggs. This is a fund that is intended to finance their retirement where there's no longer a periodic income from a job. Some households have nest eggs to fund their children's college education for 4 years, sometimes 5. You may want to bum around some foreign country for a couple of years after you graduate, not having to work, just taking in the sights, the sounds, and the culture. But you're going to have expenses such as food and shelter, and these expenses are going to continuously draw down your nest egg. So before you leave, you better make sure you know how large a nest egg you will need, based upon your recurring expenses, how long you'll be funding those activities, and the rate of return those savings will generate. Let me demonstrate this concept with a graph. Suppose that in year 0, the year before you went on your trip, you had some money in your nest egg fund that you had already saved up. The amount of money is indicated by the height of that green stack. Envision that as a bunch of $1 bills stacked on top of each other. In the first year of your trip, and we'll make all of these calculations annual just for convenience rather than monthly, you'll draw down that nest egg by a certain amount, which is indicated by the red circle. And you'll draw this down in order to fund your activities like eating and sleeping somewhere. By the end of year 1, and remember, with a conventional annuity, we're talking about payments and deposits at the end of the year. So by the end of year 1, your nest egg would be diminished down to the height of that blue stack, except for the fact that throughout the entirety of year 1, it was earning interest or some other form of return on investment. That return on investment is income that would add back to the height of the stack, the amount of which would be based upon the rate of return you were earning. And then, at the end of year 1, you'd withdraw the same amount, which would, of course, decrease your nest egg down to the height of the orange stack, except for the fact your nest egg was earning interest throughout the whole of year 2, which is indicated by the purple box added to the orange stack on December 31st, 11:59 p.m. of year 2. And this process of drawing down and building back continues from period to period. Notice 2 things. First, the interest earned from one period will be less than the interest earned from the previous period. And that's because the principal, which is the amount that's earning the interest, is shrinking every year. Second, and even more important, the size of the withdrawal is greater than the amount added back through interest income. Therefore, the heights of these stacks will continue to decline. In what year will your nest egg be completely depleted? That is, how long will your nest egg last? A rough and dirty way of estimating that amount would be to divide the annual withdrawal into the original nest egg, and the result would be the number of years it would last. And this probably wouldn't be too inaccurate if you were only going to fund the activity for maybe 3 or 4 years. But if you were going to fund some activity for, say, 5 or more years, you need to use the present value of an annuity formula to account for the fact that interest income adds back to the stacks every year. Suppose, for example, that you were saving up to fund your retirement. It's not at all unusual for a person to live a retirement life for 30 or more years, and that's what you'd be hoping for. But dividing your planned withdrawal into your original nest egg is going to give you a result that's way too low. Over a 30-year period, the interest income is going to add a significant amount back to your nest egg. The result will be that your nest egg will last you for a much longer period than the rough and dirty method had indicated. Consider the following example. Suppose that you felt that you could live a comfortable enough lifestyle by withdrawing, say, $100,000 a year from your savings. Again, we'll keep this on an annual basis to make the math easier. The real value of $100,000 won't be very much by the time you retire. If you plan on withdrawing this amount, you either plan on living a very simple lifestyle, or you anticipate having other sources of income, like Social Security or rental income from some real estate you own, supplementing the income from your nest egg. To be honest, I wouldn't rely very much on Social Security if I were you. You'll need to acquire some revenue-generating assets during your working years. Okay, so you want to withdraw $100,000 a year from your nest egg account. Suppose also that you could get an annual rate of return on investment of 8%. And also assume that you want to make those withdrawals for 30 years. So you can see here our parameters. The annual withdrawal from the nest egg is $100,000. The annual rate of return on investment is 8%. And the years from retirement to death, at which point your nest egg will be drawn down to zero with the last withdrawal, will be 30 years. How large must your nest egg be in order to fund your retirement? According to the rough and dirty method, you'd need $3 million. But this method neglects the fact that what remains of the principal year after year continues to draw interest. For an accurate computation, you'd need to use the present value of an annuity template. Let's plug in the values that we know into the variables. The payment, $100,000, R, 8%, N, 30 years. As you can see here, I had to add a 30-year row to the table. The PVIFA for 30 years at 8% is 11.258. So, multiplying the PVIFA by $100,000, we see that if you can get an 8% average annual rate of return on investment, you'll need a nest egg of $1,125,800 to provide you with $100,000 worth of income for 30 years. But you won't be able to leave any of the rest of it to your kids, though. It'll be gone. You can see just how inaccurate the rough and dirty estimate was and how it so badly overstated your retirement needs. And the longer the time period, the more inaccurate it will be. Let's look at a variation on this theme. Suppose you could only get a 5% annual rate of return on investment. How many years would that $1,125,800 nest egg pay you $100,000 a year before it was completely exhausted? Okay, so here we will plug in the values that we know into the present value of an annuity template. Moving that $100,000 to the other side of the equation and dividing it into the nest egg, look down that 5% column and find a coefficient reasonably close to 11.26. Pause the video and see if you can find it. And there it is, 11.274. That's about as close as you're going to get using the tables. And from there, we go across that row over to the years column, N, And what we see is that at 5% rate of return on investment, that nest egg is only going to last you for 17 years before it is completely depleted. Here's another variation. Suppose you could get a 10% rate of return on investment. How much could you withdraw per year from your $1,125,800 nest egg if you only needed it to last for 15 years? Okay, filling in what we know into the present value of an annuity template, going across the 15-year row and down the 10% column to find the PVIFA, which is 7.6061, and then dividing the PVIFA into the nest egg, we get $148,013. So if you have a $1,125,800 nest egg on which you could earn 10%, and you only needed it to pay you for 15 years, you could withdraw $148,013 per year before it was drawn down to zero at the end of year 15. Be sure to get some practice by downloading these two documents in the to-do list of Module 2, the Time Value of Money Practice Problems and TMV, Time Value of Money, Word Problems with Solutions. Check those out. If you have any problems with any of those, please post a question or comment in the Module 2 forum on the discussions board.